Well, first of all, thank you, Captain Johannesson, for bringing all these people to my Arctic waters.
So, what's happening?
We're counting the hours until we can go home.
But where are we now?
We're on our way to Bergen and it's 10 to 12.
When will we get there?
At 2:45. And then we have to leave at 3:45 a.m. to the airport for a 6 o'clock departure. And we get home landing in Miami at 2:45 in the afternoon. So we go from 2:45 to 2:45 to 2:45.
But it's 2:45 plus 6, right?
Yes.
Hey, here's what it looks like outside.
Hi, I'm Helga Christensen.
Hi, I'm Tudor Morgan. We are expedition leaders for Hurtigruten. Today, we're taking a look at the science behind Northern Lights. But first, let's get a quick introduction of what Northern Lights actually are. Can you start, Helga?
Absolutely! Northern Lights is a natural light phenomenon in the night sky. In Latin, they're actually called aurora borealis, that literally translates into the northern dawn. Aurora was the Roman goddess of dawn, and boreal means northern. This is why the northern lights are often referred to as auroras. These lights are most commonly seen in the polar regions, meaning that than the Arctic and Antarctica. But in Antarctica, the light is called aurora australis, which means the southern dawn.
Most auroras occur in a belt known as the aurora zone. These two zones stretch around the northern and southern hemisphere as a 2,000 kilometre stripe in a latitude 10 to 20 degrees from the geomagnetic poles. In the Arctic, these mesmerising lights are most likely to be seen above the Arctic Circle. There are several reasons for this. First of all, there are the polar nights this far north in winter. Polar nights mean that the sun does not rise above the horizon. It's basically pretty dark there, and further north you are, the longer this darkness lasts.
To give an example, in Ernest, just above the Arctic Circle, they have a little bit under 2 hours of daylight when it's winter. But at the North Cape, which is almost the northernmost point in Norway, there is no daylight whatsoever from around 20th of November until the 22nd of January. That means 2 whole months of darkness. On the other hand, they have no night from May 12th to the 31st of July. The phenomenon is known as the midnight sun.
Short days and long nights make it easier to see the auroras in the sky between October and March. But what causes them? Let's talk some science.
Well, okay then. Well, the northern light starts on the sun, situated 149,600,600 kilometers away from Earth. The sun constantly produces a lot of energy. Sometimes there are solar eruptions on the surface, and these eruptions causes solar winds that consist of high-speed electrical charged particles, also known as plasma. These charged particles, is basically just thrown out into the interplanetary space and beyond.
These winds travel through space in a very high speed and will reach Earth after 1 to 3 days. Luckily for us here at Earth, we have a magnetic shield that surrounds our planet and forms what is called the magnetosphere. The magnetosphere deflects most solar particles before they reach the Earth's atmosphere. Without it, the particles from the sun would have stripped away our atmosphere and the oceans.
The shape of the magnetic shield constantly changes due to the bombardment of the solar particles which is sent out from the sun. But even with this shield, the solar particles, they connect sometimes with the magnetic field, and they traveled on the magnetic field towards the polar regions. And this is when the magic happened. The particles are drawn towards the magnetic north and the magnetic south pole, and it produces rings of emission around them, known as aurora ovals or zones.
The particles hit the atmosphere as a result of this bombardment. The oxygen and nitrogen atoms in the atmosphere will emit light. And this is seen as the northern lights here on Earth. Just look at it. Beautiful, right?
The colors of the northern lights are determined by whether the charged particles collide with oxygen or nitrogen atoms as it enters the atmosphere. Also, it depends on the altitude on which the collision occurs and the speed of the atoms when it collides with the particles. You'll get green auroras when the particles collide with oxygen atoms at altitudes between 120 to 180 kilometers.
The northern lights appears in purple when the particles collide with nitrogen atoms and in higher speeds at altitudes around 120 kilometers. And finally, the aurora will be blue when the particles collide with nitrogen atoms at altitudes below 120 kilometers.
Due to these extreme altitudes, you will not see the northern lights when it's cloudy. That's why being on a ship is so brilliant when you are hunting the northern lights. First of all, you are away from disturbing electric lights. If you're standing in the middle of a city, the lights from houses, street lights and such will make it much more difficult to see the lights in the sky. Also on the ship, you're constantly on the move, meaning there's a much bigger chance to outrun the clouds and go to an area where the sky is clear.
What I find so amazing about the auroras is all the shapes they come in. We mainly categorise them in 5 different types. First, you have the glow, also known as the diffuse aurora. That is northern lights in the simplest form. They resemble a part of the sky that reflects moonlight or city sky, but there are no clouds. They can be quite hard to see with the naked eye.
Then you have the arcs. They look a little bit like a rainbow and span from one horizon to the other. They can be diffuse or structured with rays. And they mostly appear either when the northern lights are quiet or growing in intensity. At low latitudes, this magical light show usually begins with an arc in the horizon. The arc will appear differently if you see it from afar or if you're situated right beneath them.
Then you have the drapery auroras, also called curtains, bands or ribbons. They will appear as swirls that folds or even look a bit like a snake that moves across the sky. The drapery can move slowly or with moderate speed. And when the northern lights intensifies, they start dancing. When you see these, it's usually a sign of active auroral conditions, meaning there will be lots of them.
The northern light pillars are spectacular features. They're also known as beams or rays, and for many photographers and northern light hunters, they are on the bucket list. The reason for this is that seeing them from a distance, you can usually see the whole height of the aurora. Standing right beneath the pillars, it will look like a vortex of northern lights are opening up above your head. Just imagine how incredible that is.
Then, as a grand finale, the ultimate goal is seeing the northern light coronas. They are the brightest, most colourful and fastest auroras, with rays emanating in every direction. The only problem is that they are quite rare, so seeing this elusive phenomenon will be one for the books.
You can use several apps or websites that forecast the northern lights with quite some accuracy. They use sunspot activity to measure the geomagnetic activity in the atmosphere. With some certainty, they can predict where the particles from the sun will hit the atmosphere and where then, of course, the northern lights will appear. But even if you are at the right spot at the right time, it's never certain you'll see them. Clouds is one big obstruction. Another is how bright the auroras will shine.
The intensity of geomagnetic activity will also affect how bright the northern light will shine. To measure this activity, we use something called the KP index. The index goes from a scale from 0 to 9, when the 9 represents a huge geomagnetic storm, meaning our atmosphere is bombarded with particles from the sun. A scale 9 on the KP index is very, very rare and happens approximately 4 days every 11th year. The few times we have geomagnetic storms on scale 9, the northern lights will shine so bright it will be visible in the south of England, central France, Texas in the US, and northern Mexico. So this is why the further north you are, the bigger the chance is for seeing nature's own light show, because northern lights down to 1, 2 and 3 on the KP scale can be seen here.
Quite impressive, right? So why don't you come and hunt the light with us? Either on a winter cruise or expedition along the Norwegian coast, or on a land-based adventure to Svalbard. Even if you now know what causes the northern lights, we promise it will be a totally magical experience.